All right, let's talk about polysaccharides. Polysaccharides are made from sugars. So sugars are our monomers. And kind of there are lots of examples of polysaccharides, but the two most common ones are cellulose, which is responsible for the structure of trees and the rigidity of trees, and then glycogen, which is in means of storing glucose in the human body. So to talk about polysaccharides, we're going to draw a sugar, and I don't want to draw my sugar that way. I want to draw it this way, because this way everybody draws it. Okay, so this is glucose. We're going to put our OH groups equatorial. And let's say this glucose is actually already attached to something. So here's off this OH is not really an OH, it's an OR, and it's a growing chain. And we want to connect this glucose to another glucose. And that will make a new connection, and it will exemplify other connections that we could make. So we'll show one connection, but of course we're talking about making thousands or tens of thousands of connections. So what has to happen? In polysaccharides, the chemistry normally happens at the anomeric center. So at the sugar, that is the one carbon that has two bonds to a more electronegative atom. We have lots of bonds to electronegative atoms, but only one carbon has two bonds. And so somehow, under some kind of pseudo-acidic conditions, this OH gets protonated or activated and becomes a leaving group. And actually, this oxygen, that second oxygen, pushes that leaving group out. And that is going to get us to the exact same structure, kind of anticlimactic. We're going to get the same thing, except we form this oxonium ion. And oxonium ions are good electrophiles. So now we have another sugar and another glucose. And this glucose is full of weak nucleophiles, oxygens, and one of these nucleophiles, I'll pick the one on the 4 carbon, can attack our oxonium ion, and now we're going to make a new CO bond there between this oxygen and what was our anomeric carbon. I'm going to skip a step here. I'm going to simply remove this H off of the 4 position. So here is our original glucose. That's our original monomer. This has now been attacked by our second glucose monomer from the 4 position. And now we've made a connection, a linkage, between our 2 sugars. And there are ways to classify these linkages. Are they alpha? Are they beta? This one is shown beta. And which carbons are connected? This happens to what we call this a 1,4 connection. I don't want to get into the details of that, but there are different ways that these could be connected. But this is a linkage in the polymer. Just like an amide linkage we'd see in a polypeptide, this is a different linkage. It's actually not an acid derivative, so it's one example of a condensation polymer that does not involve acid derivative, but it's still considered a condensation polymer. So this can continue. And so in the body, one reason we make these types of condensation polymers, polysaccharides, is in the upper right to talk about glycogen. So if you have an excess of glucose in your body can store up that excess glucose. You don't just store it as glucose, you actually package it into a more compact form. And that compact form is a polymer of glucose. And so glycogen is a polymer of glucose. Now, this polymer would be worthless for energy storage if we couldn't run the polymerization backwards and get back all the glucose. Turns out your body can do that and do that very readily. So when you run low on glucose, your body says, we need more glucose. And what it does is it looks for its glycogen, unzips it, gets back the original glucose, and then your cells can uptake that. And your metabolism can run and you can keep on trucking. So those are polysaccharides. It's an example of a biopolymer, condensation polymer.